do that, you can then derive all the areas that are represented by this distribution, any areas that's represented by this. And in fact, we have a table that we can use to calculate that. Okay, so let me bring our files up, and this is on Blackboard again, and you can get to this as well. I'm going to go to this table, Z tables, Agreste. Agreste is the name of a textbook that we used. You can use the one in the back of your textbook. It looks almost identical to this table. This is one that I happen to like to use. So I'm going to open this up, and notice what we have here. We have actually two pages of tables. We have a page here, and we have a second page here. And if I'm going to take a look at this first page, you'll notice that there are a whole bunch of numbers underneath this thing called Z, the Z-score, right? And then there's numbers to the right of it. There's actually 10 numbers to the right of it as well. These numbers on this first page are all negative numbers. What these numbers represent is the number of standard deviations away from the mean. So one standard deviation away from the mean would be right here. Well, if you have a more accurate measurement of the number of standard deviations, so for instance, in our case, we're looking at 0.67, 0.67 standard deviations away from the mean. Well, this is unfortunately on the negative side, but trust me for a moment. On the negative side, if I were looking at negative 0.67 standard deviations to the left of the mean, I would be using 0.06 for my first digit, and then walking over in that row to get the value that's representing the 7 as the third digit. So that's would be the last digit would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in other words, if I were interested in a standard deviation that was negative 0.060, I'd be using this number. Negative 0.067, I'd be using 0, 1, 2, 3, 6, 7. I'd be using this number. 0.069, I'd be using this number. Negative 1.65 standard deviations would be 1.6, and then 0, 1, 2, 3, 4, 5. I'd be using this number. You can see that, right, where they intersect. Okay, what do these numbers, these 4-digit numbers represent? These 4-digit numbers that I locate using the standard deviation, they represent the area that is determined by that Z-score, by that number of standard deviations. So how do I know what area that is? Well, this little chart gives you an understanding of what area is represented here. So the area that's represented here is the area that's between the Z-score that you've chosen and the rest of the distribution. So in other words, if our Z-score was negative 0.67, okay, let's see, 1, 2, 3, 4, 5, 6, 7, then 25%, 25.14, or 0.25, or 25% of the distribution would have been to the left of that Z-score. Now, our Z-score is 0.67, but it's not negative 0.67. It's positive 0.67, which means it's to the right of the mean. So I'm going to go to this positive page with all the positive values. And I'm going to look up and notice that when the Z-score is 0, that's the mean, 50%. So in other words, 50% of the area is to the left of that value. Okay, so let's take a look at what our value of 0.67 will be. 0.060, 1, 2, 3, 4, 5, 6, 7. It looks like it's about 75%. So it's telling us that 75% of the distribution is to the left of this value. In fact, if I want to be more accurate, it's really 74.86, 0.7486. So I'm going to go back to my chart. And now I know from that chart that 0.7486, that portion of the temperatures for the males, people in this population, are below 99 degrees. The question asks us, what's the probability of randomly selecting someone that has a temperature above 99 degrees? Well, all I'm going to do is take 1.0000 and and subtract the area I don't want, the area below 99, from that 0.74864125. So 25% of the population has a temperature higher than 99 degrees, or you could say the probability of choosing an individual from this population that has a temperature above 99 degrees is 0.25. Okay, are you guys comfortable with that? Have I lost any of you on that? I'm going to go back now and do the next problem. Next problem is going to be less than 98 degrees. Okay, so let's go back here. Okay, what about less than 98 degrees? Okay, so 98 degrees is going to be here, right? And what is the z-score for 98 degrees? Well, remember, z is equal to x minus mu over sigma, right? So that's going to be 98 minus 98.6 over 0.6. Well, I got lucky there, didn't I? So 0.6 over 0.6 is equal to 1. Did I use the right number there? Yeah, 98 degrees. Okay. So that's 1. So I'm actually going to, instead of using, this is 74.7, I'm sorry, 0.2514 is this area in here. Okay. Instead of using the empirical formula, even though I could, I'm going to use the more accurate table. So this is going to be -1 standard deviation. So let's see what area that represents. Okay, let me find my table. Here we go. So -1, -1.0 is going to represent 15.87% of the distribution. Let's go back here. This is going to represent 15.87% of the distribution. Well, notice something. I didn't really draw this further enough to the left. Notice something. This number, because it's the way the chart is made, this number represents the area below 98. Okay? We don't need that. Okay, that's we just used that before. So the probability of choosing someone that has temperature below 98 degrees is about 16%, same as our empirical formula would tell us, except we have it a little bit more accurately here, 0.1587. Probability of choosing someone that have a temperature higher than 99 degrees is 0.2514. Okay, so good. Let's take a look at the next question. Okay, get back to the problem. Okay, the probability of someone having a temperature less than 98 or greater than 99 degrees. Okay, less than 98 or greater than 99 degrees. Well, what's going to satisfy that? What's going to satisfy that is either one of these areas, less than 98 or greater than 99. And that's going to be 0.2514 plus 0.1587. If we add those together, that's those two areas that we're interested in. 1 carried 1, 1, and that looks like about 41%. 41% of the population is either less than 98, or greater than 99. That's pretty interesting. And the last question was, and I'm not going to go back to it. The last question was, what's the probability that you would randomly choose someone that's between 98 and 99 degrees? In other words, this area that's left in here. Well, we know that this accounts for everything but that area. So I can just take 1.000 and subtract 0.4101, 0.4101, and that's going to give me 9 and 9. And let's see, 9, 8. Let's see, 6899. Is that right? I think that's right. 58, 58. That's going to be 58.99, about 60%. of the distribution is going to be in here. Okay. Are you guys okay with that? Does that make sense to you? It's a little bit more tedious than the last question, isn't it? Okay, so I'm going to, you have some of the problems to practice on there, but I want to move on to another kind of distribution, and that's called a binomial distribution.